All right, so step 3, calculating our test statistic. Remember this? Oh yeah. Back to chapter 5. So I'm just going to go ahead and breeze through this, review chapter 5 to see how you work through this again. But really, this is how I'm going to be given the data. You're going to have data for your individuals. And remember, each individual has data for both variable x and variable y. So in this case, how many people do we have in our sample? We have 10. So go ahead and work through calculating the rest of this table here, where you get x squared, y squared, x sub y, and then don't forget your summations, because the summations are really what you're going to be plugging in to this formula here. Once you've filled out the table, go ahead and work through calculating R. Unpause the video once you've worked it all out to confirm that you got the correct answer, and round 3 decimal places to the right for your final answer. Alright, so let's see how you did. So let's take a look at the table. So we have all of our data for x squared, y squared, and the product of x, y for each of our 10 individuals. And then we just go ahead and add up all of those columns. And then we just plug and chug, right? So here we go. And once we plugged everything through, we should get a final correlation coefficient of 6.92. Did you get that answer? Hopefully you did. So that would be step 3 for the hand calculation. So now let's take a look at how we get our test statistic from SPSS. So I want to go to Analyze, and because we're doing a correlation, we go to Correlate, and we have 2 variables, so that's a bivariate correlation. And once you click on bivariate under Correlate and Analyze, you'll want to go ahead and choose the 2 variables that you're going to investigate, and move those over under Variables, and then click on Options. And once you've clicked on Options, you'll want to go ahead and select means and standard deviations. We want to get some descriptive statistics of both of our variables, because that'll allow us to go ahead and write out our conclusion. Otherwise, we won't know any descriptive statistics for either of our 2 variables. So once we've selected our descriptive statistics that we want, continue, and notice that we have different correlation coefficients. We have Pearson's, which will be checked by default. We have Kendall's tau B, which is something that we're not going to learn in this class. And then we have Spearman's. And remember, when do we use Spearman's correlation coefficient? When both of our variables are ordinal in nature. And then we see we have our significance. We have 2-tailed, or we can do 1-tailed again if the research question is asking for any particular direction. Then we want to go ahead and change it to 1-tailed. And then we'll see that SPS is so awesome that it'll actually flag significant correlations for us. So go ahead and click on OK, and then we'll get our output. So here we have our descriptive statistics, and I just threw in here a couple other variables that we've seen before in terms of other drugs, other substances used. And again, if we didn't select our options for SPSS to give us this data, we're not going to be able to talk about the descriptive statistics of our variables, nor be able to get the sample size which we're going to use in order for us to calculate our degrees of freedom. So here's our correlation matrix. Recall that there's redundancy here in this table. So if we have here, we see each variable lining up with each one of them, and we see that the sample size is how many people took that particular substance. So we see 369 people drank alcohol, 273 people smoked a cigarette, 22 people used OxyContin non-medically. But really the redundancy again is that we have the same information in this lower triangle than we do in the upper triangle. So it's just a matter of looking at one of these two triangles to get your data. So let's take a look at our actual research question of alcohol use and first smoked a cigarette. So we see we have our Pearson's correlation coefficient, 0.452. And then we see we have our sig. And what does sig stand for? Our p-value. So our p-value is 0.000. So now that we have our p-value, 0.000, we can go ahead and use this and compare that to what to make our decision? To alpha. So here's our rule. Remember, if p is greater than our alpha, then we're going to fail to reject the null, which means we're going to accept the null. But if our p-value is smaller than our alpha level, then we're going to reject the null and accept the alternative. So in this case, our p-value is 0.000, which is smaller than our alpha, 0.05. So we're going to reject the null hypothesis. And we see that we have SPSS has those two little asterisks right behind 0.452. And if we look down here at the bottom, we see that the correlation is significant at the 0.01 level, compared to if a Pearson's correlation coefficient has just one asterisk, then that's SPSS is telling us that it's significant at the 0.05 level. So this is very significant. Now we would just walk through step 3 and step 4 when we have our SPSS output. And so let's run through the tools that we need in order for us to make our decision when we have a hand calculation. So let's say we hand calculated our R value and we got 0.452. Then we need to have our significance level. What's our significance level? 0.05. And given our research question, how many tails are we investigating here? Are we investigating 2 tails or 1 tail? Well, because we're just looking at whether or not there's a relationship between alcohol and cigarette use, we're doing a 2-tailed test. So our next tool that we need are degrees of freedom. So let's take a look. Bobby the Bear, what are degrees of freedom for correlation coefficient? Degrees of freedom of correlation coefficient is equal to total sample size minus 2. Thanks, Bobby the Bear. So note that whenever we're calculating our degrees of freedom for correlation coefficient, we have to look at the sample size for that particular analysis. So how many people drank alcohol in our total sample? 369. But how many people smoked a cigarette and also drank alcohol? Because these are the people in our analysis, because we want to know the relationship between alcohol and cigarette use. So how many people do we have in our sample of alcohol and cigarettes? 257. So we use that in our degrees of freedom formula to give us a total degrees of freedom of 255. So now we have our third tool, our degrees of freedom. So the last tool that we need in order for us to make our decision is our critical value. So let's take a look at another table. Oops, not a foosball table. Oh, that's fun. But this table. Values of the correlation coefficient needed for rejection of the null hypothesis. Okay, so here's the tools that we have so far. We have our 2-tailed test. We have our alpha level, and then we have our degrees of freedom. So go ahead and pause the video and see if you can find the critical value, and then unpause it to see if you got the right answer. Okay, so since we have a 2-tailed test and our alpha level, we'll look down this column. And since our degrees of freedom is 255 and we see that our table only goes as far as 100, then we go to the last row and we have our critical value of 0.1946. And notice that it's plus and minus because we're doing a 2-tailed test, so we have 2 critical values. So now we have our last tool. So thanks, Tom the Tool Man. Let's go ahead and actually make our decision. So here is our rule for making our decision, whether it's 1-tailed or 2 tails. That if we have a 2-tailed test, we have two critical values, a positive and a negative. So if we have a negative critical value, because we're testing and looking at a negative R, if our R value is smaller than our critical value, we accept the alternative hypothesis and reject the null. If we have a positive R value, we compare that to the positive critical value. And if our R is greater than our critical value, we reject the null and accept the alternative hypothesis. So given our data, here's our critical value of 0.1946. And since we have a positive R, 0.452, we see that that actually falls within the rejection region. So if we were going to write out our comparison, we have our critical value and our R, and we see that our R is greater than our critical value, so we reject the null hypothesis. So now, since we've gone through steps 1, 2, 3, and 4 in making our decision, we can go ahead and state our conclusion. So whenever we report our results for correlation coefficient, we always report the mean standard deviation for each variable, your test statistic, your degrees of freedom, and your p-value or significance level. And if you have significant relationships, then you also report the strength and direction of that relationship. So here's our interpretation. There was no significant relationship between our IV and DV. We have our degrees of freedom, our R statistic, our p-value. But if we have significant relationships, then we want to state it as there was a significant weak, moderate, strong. So we're talking about the strength and also the direction, direct, indirect, positive, or negative relationship between our IV and DV. Okay, so given our example, here is our conclusion. There was a significantly moderate direct relationship between age of first use of alcohol and age of first use of smoking cigarettes. And we have the mean standard deviations for both of our variables. R is equal to 0.452 with 255 degrees of freedom, and our P is equal to 0.000 because we know our p-value from our SPSS output. If we didn't know that, we would just simply put P is less than or equal to 0.05. But because we had significant relationships, then we also want to go ahead and calculate, report, and interpret big R squared. And do you remember what big R squared stands for? This is our coefficient of determination. Remember, it's a much more precise way of interpreting a correlation coefficient, and it describes the amount of variance that these two variables share. So the way we calculate this is to just square little r. And we use a template that their IV accounted for so much percent of the variance in the other variable. So here's our work. 0.452 squared is equal to 0.2043. Multiply that by 100 to turn that into a percent. So we report age of first use of alcohol accounted for 20.43% of the variance and age of first use of smoking cigarettes. So putting it all together, here's our research question. Is there a relationship between the age of first use of alcohol and the age of first use of smoking cigarettes? Yeah, there was a significantly moderate direct relationship between age of first use of alcohol and the age of first use of smoking cigarettes. These statistics. Age of first use of alcohol accounted for 20.43% of the variance and age of first use of smoking cigarettes. That should be your final answer. Again, showing your calculation for big R squared, your coefficient of determination.